Have you ever wondered why the door handle is on the end of the door, or why it's easier to unscrew a bolt with a wrench? No? Well, if you were wondering that, it's because of torque. So the torque can be defined as the radius times the force that you apply times this sine of theta. Okay? So torque we usually define as this tau guy here. And so if we want to find the units of torque, the radius, which is in meters, times the force, which is in newtons, and the sine of theta won't have a unit, so we'll express it as a newton meter, is what you'll commonly see for torque. So let's see three examples. So we have like a beam that's able to rotate along this hinge here. And so let's say the force is applied at an angle right at the end of this R. The torque for this case, we would have an angle of 90 degrees. The angle is from the force to the radius. So since this is 90 degrees, the sine of 90 is just 0. Nope, sine of 90 is just 1. So the torque will just be radius times force. But now in this case, we have some angle right here. So now the torque will have to include the radius times force times the sine of theta, which is going to be something less than 1, so it's going to reduce the torque. So now if we pull all the way so that it's 180 degrees, well, now our torque is the radius times force times the sine of 180, and this just equals 0, so our torque equals 0. And so what might seem intuitive already is that when you apply force at this perfect 90 degrees, you're able to cause this beam to rotate. And the more closer to 90, the easier it is to rotate, and if you pull it directly out, you're not going to get any rotation. So that's basically what this torque is doing, is showing how much force you're applying to rotate the beam, and it will relate directly to that angular acceleration. So let's talk about how we can use force diagrams for this. So let's say we had a situation where there was like a wall and there was like some beam coming off of it, and let's say we wanted to calculate like the net torque or something. We wanted to use like a free body diagram. So usually a free body diagram just has one point and we have like some forces coming off it like this. But in this case, our forces might not be at the same point. So we may have the gravitational torque, which we can approximate at that center of mass. So that's one force. And maybe let's say someone is standing on it, so they're applying another amount of torque on this board. And then maybe there's like a cable or something, and this applies a force. So we can draw out this sort of free body diagram, and now for each of these forces we have a radius. And now we have a bunch of different torques that we can sum up to get the net torque. And so for the example of a door hinge, let's say we have like a door like this, and it's able to rotate along here. If this is the hinge, if you apply a force to open the door at the very end, you get this force times this radius that's large. Let's have a capital R equals the torque. But if you apply it right near this hinge here, your force is going to be a very little radius to give the torque. So to increase your torque, it's directly proportional to the radius that you apply it at. So the closer to 90 degrees and the closer and the farther from where it's rotating from is going to give you the most torque. So that's the overall conceptual ideas of torque. So now let's apply it to an example. Okay, so we have Bob holds a tree of uniform mass at an angle of 15 degrees from the horizontal. The tree is 500 kilograms and is 5 meters long. What is the torque due to gravity? So we're only trying to find one torque here, and it's the torque that's applying the tree due to gravity. Okay, so let's first draw a little picture. So let's say we have Bob right here. You know, he's holding a tree. We'll say this is like the ground, and he's holding this tree like this. So we don't care about any other forces that are applying here, but we know that gravity is applying at every single point on this tree. Gravity is being applied, right? But it would be very difficult to find the force at every single point and to give a bunch of r's. And what we end up doing is to find this center of mass. That's pretty much what we do to the masses. And if we wanted to find the net torque just due to gravity, we could integrate along this whole tree and find the average at every point. But it turns out we can actually just approximate it as the force being applied just at the center of mass, which, since it's a uniform mass tree, we can assume it right in the center of the tree. So this is the force due to gravity, and that's the force we want to look at. And so so now let's write our variables too. So we have the mass of the tree, which is 500 kilograms. We have the length of the tree, which is 5 meters. We have the angle, and I'm going to call this angle with the earth, angle E, I guess. And that's 15 degrees above the horizontal. So we have this angle right here. And that's angle of the earth. Okay. And so we also know gravity equals 9.8, obviously. And so we need to find the torque due to gravity. So the torque, in any case, is just the force times the radius times the sine of theta. So we want to find the radius. We need the force, which we already discussed. This force due to gravity is what's going to cause the torque, so we can say Fg here. And we want sine, and I'm going to call this theta g, since it's not necessarily this angle, because it's the angle it makes with the radius. And so what is the radius? Well, it's not going to be the length of this whole tree, because the force is being applied right at the middle. So this radius here is going to be 1/2. So the radius will be just the length of the tree divided by 2. But then we need this angle, and so I'm going to just blow this little piece right here up into a larger triangle. Right? So we know that the force due to gravity is this piece right here. This is the angle of the earth, and this is a 90-degree angle. So we need this theta g right here. So how can we get this? Well, we know the interior angles of a triangle is just equal to 180. So if we go ahead and sum up our angles, we know that it has to be the total angle of the interior angles minus each one of these will give us that. So the angle of Earth, and then minus is 90, and so we know that the angle of the Earth is 15 minus 90, and if we plug these in, we get 75 degrees. Oops. Should be 75 degrees. Okay. So now that we have that, we know what our angle theta g is. So now we can start plugging some more variables in. So we said r is 1/2 the length. Our Fg is just mass times gravity, because that's always what mg is. And we know the mass and we know the gravity, and then the sine will be that theta g, which we just found. And now we have all these variables, and we can simply just go ahead and plug these in. So the length is 5/2, the mass is 500, times 9.8, times sine of this theta g, which is 75. And so if we plug these in for our torque, we get this value right here, Newton meters. And so that's the torque just by gravity on this tree. Okay, now let's do one more example here. So we have, what is the net torque about this point C, which is the center point of this diagram. So we can think of this as one solid object that can rotate on this circle and the outer circle. And these are each forces, these three forces that are applied. So let's just start by labeling the forces. We can say this one is force 1, this one can be force 2, and this one will be force 3. And so we need to find the net torque. Now the biggest thing here is that we need to know what direction each of these forces are going, because if a force is going counterclockwise and one is going clockwise, those aren't going to be helping each other. So let's try to define what the net torque will even be. So we know the net torque is just equal to the sum of the torques, right? That's simply just saying we sum them up. So in this case, let's look at torque 1. So torque 1 is going to be this one at force 1, and it's going in the counterclockwise direction because it's on this circle here and it's going this way. And we talked about in a previous video, counterclockwise direction when we talk about rotation is the positive direction. And really we could define either one as positive, but it's very typical to have counterclockwise as positive, so we will denote it as such. And so this one we can just leave as it is, but now we have our next torque, torque 2. But torque 2 is going clockwise, because it's going, around the circle like this. And so since it's going clockwise, we actually have to subtract this torque and make it negative. Okay, so then our torque 3, which is on the same outer circle, also going clockwise, because it's on the bottom going to the left, it'll also need to be subtracted. And so now that we have our correct directions, we can start plugging in what would be the torques. And so we know that we're going to have, let's just say radius 1 force 1 minus radius 2 force 2 minus radius 3 force 3. And so now we also need to make sure that our why don't we put the sine of theta in here? Well, each one of these forces are tangent to this circle. So if we say this is like the radius for this radius 1, this angle is just 90. And so this one is trying to throw you off. It says it's 30 degrees from the top. We don't care about the top. This top doesn't mean anything. We just care about where's this force on the circle, and there's this radius here, radius 2, and this angle is also going to be 90, and same thing for this force. And since all these are 90, sine of 90 is just 1, we can just disregard the sine of theta because it's perfectly perpendicular to the radius. Okay, so that's why we don't need that. And so now we need to determine our radiuses, which should be pretty simple. Radius 1 for this force right here is just this inner circle, which says 0.2. So we'll plug that in, and force 1 it gives us as 10 newtons, minus radius 2, which is this outer circle, which says is 0.5. So we have 0.5, force 2, which right here is 5 newtons, and then radius 3, which is also 0.5, is 8 newtons. And so if we plug this in to get our net torque, we just get a negative 4.5 Newton meters. And so what does this negative mean? Well, we define negative as the clockwise direction, so we could also say the answer is 4.5 Newton meters clockwise. And then we won't need that negative because that negative is really just the direction of torque. Okay, so that's what we got for torque. In the next video, we'll kind of shift gears a little bit and talk about the rotational inertia, so make sure you stick around for that, and then we can combine torque and rotational inertia to get angular acceleration and see how Newton's laws apply to this rotational motion. Alright, so leave your questions down below, and thank you for watching.